Number 27 says solve the system of equations using matrices. Use Gaussian elimination with back substitution. So the first step to use Gaussian elimination is to create our augmented matrix. I list the coefficients for x, list the coefficients for y, and list the coefficients for z. Draw a line that separates our coefficients from our constants. Then we write our constants. So Gaussian elimination, our goal is to have our matrix have a 1 in the top left corner, a 0 and then a 1, a 0, 0, 1. These x's represent just random numbers, whatever number we use when we use our row reduction. So I already have a 1 in my top left corner, so I'm going to leave that alone. I do need the second number here to be a 0. So in order to make this 0, I'm going to multiply row 1 times a negative 1, and I'm going to add it to row 2. So negative 1 times row 1 is negative 1, negative 1, negative 1, negative 6. Row 2 is 1, negative 1, 2, 17. Add them together, 0, negative 2, 1, and 11. So my new matrix, the first row stayed the same. My second row becomes 0, negative 2, 1, 11. Now before I write the third row, I want to look at what I need. I need this bottom number to be a 0. So in order to make this 4 a 0, I'm going to multiply row 1 by a negative 4, and I'm going to add it to row 3. So if I multiply by negative 4, I get negative 4, negative 4, negative 4, negative 24. Row 3, 4, 1, 1, 18. We add them together. Negative 4 and 4 is 0. Negative 4 and 1 is negative 3. Negative 4 and 1 is negative 3. Negative 24 plus 18, negative 6. So there's my new row 3. Next, I work with the second column. The first number doesn't matter, but the second number I need to be 1. To make this negative 2 a 1, I need to multiply it by a negative 1/2. So I'm going to take row 2, and I'm going to multiply it by negative 1/2. My top row, I did not change it. My second row, 0. Negative 1/2 times negative 2 is 1. Negative 1/2 times 1 is negative 1/2. And negative 1/2 times 11 is a negative 11/2. For my third row, I want this negative 3 down here to be a 0. So in order to preserve it, I have to multiply the row 2 because I need the 0 to stay here. So I'd have to multiply this row 2 by a 3 and row 3 by 2. That seems like too much work. So what I'm going to do is I'm going to go ahead and just write in my row 3 as is. And I'm going to do the next one separately. So now all I have to do is multiply it by 3, and if I add them up, this will turn into a 0. So I'm going to multiply 3 times row 2, and I'm going to add it to my row 3 to make that -3 become a 0. So -3 times row 2 will give me 0, 3, -3 halves, -33 halves. I'm going to add it to row 3. 0, -3, -3, and -6. Don't worry about the fraction because we're going to get rid of the fraction a little later. So 0 and 0 gives me 0. 3 and -3 is 0. -3 halves minus 3 will give me -9 halves. And -33 halves minus 6 will give me -45 halves. So my matrix, row 1, didn't change. And then row 3 becomes 0, 0, -9 halves, -45 halves. The last step is to get this 9 halves to be 1. And if I just multiply by the reciprocal, this will happen very nicely. So the reciprocal of 9 halves is 2 over 9. So I'm going to do -2/9 times row 3. So my row 1 and 2 are going to stay the same. And my row 3, I'm going to multiply it by -2/9. So -2/9 times 0 is 0. -2/9 times 0 is 0. -2/9 times 9 halves is 1. -2/9 times -45 halves is exactly 5. Now I have my 3 equations. X plus y plus z equals 6. That's my first equation. 0x, so I don't have to put it, plus y minus half of z equals -11 halves. 0x plus 0y plus z equals 5. Since I know that z is 5, I can plug it into here. So I get y minus 1/2 of 5 equals -11 halves. And we can solve it. So I multiply 5 times a -1/2. And then I'm going to add it to the 11 halves. Which gives us exactly 3. If I know z and y, I can plug it into the first equation to find out what x is. So x plus y plus z equals 6. So I solve this for x, and we get x equals -2. So the solution to the system is -2, 3, and 5.